It's been described as the democratization of space. What was once the preserve of governments and superpowers is evolving into a truly global industry. The catalyst for this dramatic change, a new generation of satellites, some no bigger than a shoebox, that will be deployed not in ones or twos, but in their thousands. A global technological revolution is underway.
We think in the next 10 years, you'll see more innovation than we've seen in the past 50.
Driven by passionate, dedicated individuals intent on shaping a new world.
I want to create something new. I want to create something that gives me the sense of creating new life. This is why I'm here.
A greener world.
This is the last call to action, that we have to develop the solutions that are protecting our planet.
A better world.
I have a family, and when I think about the life I want them to have and their children to have, I want them to experience the world where they can travel and live without worry, and that gets me up and going every day.
Together, they are pushing engineering to its limits.
Human creativity is the most tremendous power, and if you set a target, things that you never thought possible become possible.
Creating extraordinary machines that can help the planet and humankind in the future. The U.S. Forest Service spends half of its entire budget fighting wildfires. A study into the fires of 2018 put the economic cost of just those in California alone at $147 billion. But these firefighters are about to benefit from a revolution that is happening hundreds of miles above them. In recent years, satellites have been getting smaller, smarter, and cheaper. Often referred to as nanosatellites, they have opened up the space industry to a new generation of companies and scientists who are in turn revolutionizing our ability to observe our planet and to communicate. In Munich, Germany can be found Aurora Tech, one of this new breed of space technology companies enabled by the advent of these nanosatellites.
We plan to use a constellation of about 100 of such satellites to watch for wildfires, anything larger than 10 meters across. It's part of the world's first global wildfire intelligence service, and we will be able to detect fires and report on the outbreaks within about half an hour.
Aurora Tech's system is based on years of research at the Technical University of Munich. Fitted with thermal infrared sensors, the satellites will be able to reduce wildfire detection time from hours down to minutes, and then be able to monitor them in real time, transforming not only our ability to fight them, but also our understanding of their causes.
The reason why we're able to do it right now, and we wouldn't have been 10 years ago, is because of the improvement in technology driven by the computer and smartphone industry, but also the sensor technology we are using. This has become available within the last couple of years. This new technology has kind of opened up the space industry, not just to startups like us, but also to research groups at universities, to students, to test new technology in space.
Helping to nurture this new global space industry are organizations such as Satellite Applications Catapult, a UK government-supported space innovation company which provides advice and shared testing and operational facilities.
Right now, we're seeing space pivot from where it was previously about a little bit of trying to outdo your international neighbor in terms of military capability in defense and aerospace, or understand our cosmic origins of the universe. We're pivoting to commercial space. So we go to space now to basically create an economy, to create material wealth, which we can use on Earth and we can use in space. So what's happening right now is that we're seeing companies from across the world saying, space, this is the place we need to be. This is the place we need to do things.
And at the heart of this revolution are nanosatellites. A fraction of the cost of what has gone before, their roles can be many and varied.
It might be looking at the weather. It might be looking at climate change. It could be a new type of communication. It could be listening for identification signals from vessels at sea. There's a whole host of opportunities looking down, but increasingly also looking up.
But whatever their role, they need to be able to withstand the rigors of spaceflight. Here, for example, the resonant frequency of a potential satellite component is being tested. Incredibly, these vibrations are initiating a force on some parts of the structure of up to 75 G, which is more than 25 times the force experienced in a standard rocket launch. The ability to access shared facilities such as these here at Catapult is playing a crucial role in developing new talent and expertise. The seeds for this new space industry were in many ways first sown back in the late 1990s, when California Polytechnic State University and Stanford University developed the CubeSat. Based on a 10-centimeter cube and able to be scaled up if needed, it provided a standardized specification that could accommodate off-the-shelf parts. Suddenly, a satellite was something that could be built cheaply and quickly. It was a total game changer. And it's the same specification that's being used today. In Finland, astronomer and journalist Jari Mäkinen has taken this technological accessibility a stage further.
KitSat is fully functional one-unit CubeSat. So just like many satellites that are going around Earth now on orbit, but it has been made with the parts that are not so expensive as are the parts for the real satellite.
Although not destined for space, this educational tool gives students the ability to not only build a satellite, but also to operate it in a very similar way to its space-going counterparts.
And the most exciting thing is flying it to stratosphere. You are launching it to the edge of space on a stratospheric balloon and fly it up to the 30 kilometers or more. You get telemetry down from the satellite. You can chase the payload when it is flying, and of course planning the mission. Basically, after this, you can go right away to build a real satellite or operate a satellite that is really in orbit.
Which is exactly what Jari and his colleagues at Arctic Astronautics and Finnish technology company HALD are now doing, with an extraordinary experimental mission, the launch of the world's first wooden satellite.
This is basic research. This is material science mission, just to see if wood could be used as a material for spacecraft.
The project is known as Visa Woodsat, and it's secured investment from UPM, a leading plywood manufacturer based in Finland, as well as assistance from the European Space Agency. One of the potential benefits of using plywood panels is that they don't interfere with certain sensitive monitoring equipment. And in an industry where weight is a major factor in launch costs, its plywood construction means that the Visa Woodsat will weigh less than 1 kilogram, making it one of the lightest CubeSats ever launched.
We are using plywood that has been in a thermal vacuum, meaning that it has been in a temperature of 102 degrees for a couple of days, and at the same time in a vacuum. So it is extremely, extremely dry plywood after that.
The wooden panels are also coated in a 100 nanometer protective layer of aluminium oxide, normally used on electronic circuit boards.
It is something, again, that nobody has been thinking before, but according to the tests that has been now conducted at ESTEC, at the Technology Center of European Space Agency in Netherlands, they have tested this kind of plywood, and it seems that it is even better than most of carbon fiber or glass fiber that is used actually right now in space applications. I do have here one copy of the satellite. So this is almost final design. And with this little camera, we can then take pictures of the satellite. And in fact, inside over there, we have another camera as well that is taking pictures from the inside of the satellite.
The satellite will also house sensors to detect any moisture that could be released by the plywood once in space. Using their experience from KitSat, a prototype has already been tested using a stratospheric balloon.
Many of the traditional space engineers said originally that you are crazy, this is nothing, are now getting a little bit more interested in this. After all the results we have now got from ESA and all the research that we have done ourselves as well, this really may be interesting stuff in the future.
What makes nanosatellites so powerful is their ability to work together in groups, known as constellations. But projected numbers of satellites are becoming so large that these new groups are often referred to as swarms.
So you might have a swarm of satellites where basically some satellites are generating power to provide power to other satellites which are doing communications, to provide communications to other satellites which are basically doing Earth observation or something. So that's one concept. Typically, the terminology we use, constellation, we literally mean the same way as constellation of stars. And constellations aren't anything new. Various GPS constellations have been existing for 20 years, but not on the scale that we're talking about now. These are constellations which aren't maybe 100 spacecraft. These are constellations or planned constellations of hundreds, potentially thousands, potentially more. This is about covering the globe, basically, with the equivalent of internet broadband.
Different types of satellites occupy different orbits. For simplicity, these are often broken down into three categories. High Earth orbit is used by geostationary satellites that need to stay constantly above one place over the Earth, such as for telecommunication. Medium Earth orbit is used by navigation and communication satellites. Satellites designed to monitor a particular region on Earth, and those involved in space observation. And low Earth orbit is most commonly used for satellite imaging. It's also where you'll find the International Space Station. And it's here that the current and planned nanosatellite constellations exist. But none of this would be possible without a cost-effective way to launch them.
5, 4, 3, 2, 1.
10 or 15 years ago, there were only something like 12 companies globally who were actually launching things into space, and many of those belonged to international governments and organizations like the European Space Agency. Today, we've got in excess of 300 companies globally trying to build launch vehicles of some flavor. Many of them have yet to actually build a rocket. Some of them have managed to build rockets which have spectacularly gone sideways as well as go up. Other companies who have been doing this for a while now have actually managed to create a market launching small rockets, relatively small, lifting hundreds of kilos, and effectively started to compete with the other companies offering services out there. And what this has done is it's driven down the cost of access to space.
Meaning, instead of paying tens of thousands of dollars per kilo, you can now pay as little as $5,000.
Certain companies have made space look really simple. That's not necessarily true. Space is hard. It's really hard. It's all about speed. So small rockets can't go that fast. They don't have enough thrust to go that fast. So typically small rockets will put things into the low Earth orbit. The big rockets, they can put things into high orbits. But of course, there's a different way to put things in high orbits as well.
And that is to give whatever it is you're launching into space its own small propulsion unit.
Do you want to get there fast, which can be expensive, or do you want to get there slowly, which can be cheap? But the question is how fast do you need to be there?
At Long Beach, California, Virgin Orbit are ramping up production of their rocket, Launcher 1, which instead of taking off vertically, is designed to be deployed horizontally from the wing of a plane at 35,000 feet, meaning it is able to avoid weather patterns that can often delay a launch. Measuring 70 feet long, this two-stage rocket is able to carry payloads weighing up to half a ton.
Back in 2012, we started the development on our Newton family of engines. We started building out our manufacturing facility with the intent that we were going to ramp up to something like 15 to 20 rockets in the next few years.
But the traditional way rockets have been constructed in the past meant that if they were to achieve the level of production needed, they and the rest of the industry would have to change the way rockets are made, particularly at the business end, known as the combustion chamber.
That process traditionally took over a year to build one chamber. And we need 2 of them, one for each stage. That represents a lead time that we want to look at reducing. Now, we still have to maintain the high quality because that's obviously a very critical part in us getting to orbit. So what we've looked at is a combination of manufacturing that what we call hybrid manufacturing. It's a combination of 3D printing. In some cases, we're actually doing that with lasers and material to actually deposit metals and others to actually form the structure. But then we do a number of things where we do subtractive manufacturing or typical machining. We will take that printed part and actually machine it down to get other finishes. The combination of the 2 allows us to dramatically bring down not only the cost, but the time. Things that used to take over a year, we can bring down into the realm of 1 or 2 months. It can also bring down the weight, and it can bring down the total cost of those parts.
The initial missions, which have a 100% success rate, have all taken place at Mojave, California. But the team are now developing a more portable mission control setup, enabling them to operate from what they call spaceports, based at existing runways all over the world. When it came to choosing a plane to launch from, one candidate stood out as the natural choice. When Boeing's design team drew up plans for the giant 747 airliner back in the 1960s, little could they have imagined that over 40 years after its maiden flight, it would be embarking on a whole new career in the space industry.
Something that really was helpful for us when we were investigating which aircrafts to consider and use is that it's actually designed to carry a 5th engine.
The 5th engine mount was incorporated into the design as a way to transport spare engines around the world. Although seldom used for its original purpose, this 5th pylon was perfectly positioned to take the weight of a small rocket. But there was also another advantage it held over its more modern counterparts.
The 747 itself is not a fly-by-wire aircraft, and that actually has a good advantage for us.
Which means that instead of the flight controls going via a computer, the pilot controls the aircraft manually.
As we perform this zoom launch release maneuver, we get to a very high pitch attitude at 32.5 degrees with a rapidly decreasing airspeed. We don't want a computer to think that we're in a situation we shouldn't be in and take over for us.
Launch vehicles are probably one of the most challenging things we can do in the space industry. If you think about a launch vehicle, it has to work perfectly for minutes or at most hours. Perfectly, because you are moving at incredibly high speeds. We're not commanding it real time. It's basically being controlled by a computer. And if it doesn't work perfectly, we don't get our customers into space. We have incredibly smart and dedicated people working on this problem, but I never assume that everything will go perfectly. So there's always a little bit of a knot in my stomach. Never take it for granted, because what we do is really, really hard, but we are really, really good at it.
So on launch day, I'm in the control room, so I actually start my shift about 10 hours before we get to our drop point. So the team comes in and we are working through making sure the vehicle and the plane and the ground systems are all functioning and are working as expected.
Once pre-flight and system checks are completed, the rocket is fueled and it's time to hand over responsibility to the aircrew.
We have 2 pilots on board flying the plane and 2 launch engineers that are then responsible for monitoring the rocket. And once then the whole system takes off, that crew has the full command and control capability of the launch platform and the launch system.
Despite all the cutting-edge technology and autonomous rocket systems, this part of the mission still requires the skill, experience, and hand-to-eye coordination of a human. Chief Pilot Eric Bippert.
I kind of feel like the field goal kicker in American football. At the end of a big game, the entire team has done just all this amazing work, and then it's up to one person.
This is where Eric's many years of experience of precision flying with the US Air Force and as a test pilot really comes into its own. He must position the aircraft at exactly the right place at the right time and at a speed so precise that it cannot be allowed to vary by more than 1 knot.
It's very hands-on flying. We cannot use the autopilot. We cannot use the auto throttles. There is a certain amount of pressure But to be totally honest, with the training that I've had and once we get into execution, I don't even think about that pressure. I just think about doing what I need to do, to actually release it successfully. As a test pilot, I have a lot of experience flying different maneuvers with very tight tolerances, and this is right up to par with that. After we make the inbound turn to the launch point, we'll accelerate from Mach 0.7 to Mach 0.85. So with about 25 seconds prior to drop, we'll go ahead and execute that release maneuver. That involves approximately a 2G pull-up. And we'll basically pull the nose up to 32.5 degrees. So once we're all set and all the parameters, I'll call release, release, release. And at that point, the co-pilot will reach up to a button that's mounted above the dash and press the actual release button. You feel and you immediately know that it's released because the aircraft will immediately start this nice right-hand bank turn. 5 seconds after release, there's a delay on the rocket and it'll ignite after that 5-second delay. And it's something we can't see because we're in that bank, but you can actually hear it. And it's this loud rumble, and it actually resonates, within your body. It's a really neat experience and a great chance just to look out the window and we can see this bright plume from the rocket as it heads into space. And it's special. It's a very special experience.
Although the proliferation of launch vehicles is helping to drive down costs, launching a satellite can be even cheaper if you're prepared to ride share. However, this also has a drawback. Chances are you won't be dropped off in your ideal location, and it could take many months to reach your final destination, which for a small satellite with an operational life of between 2 and 5 years represents a huge percentage of wasted time. On the shores of Lake Como in Italy, one company, D-Orbit, has spent many years developing a solution. Vehicles which can carry multiple small satellites. They are first launched by a rocket and then transport each of the individual satellites to their precise desired location. They call them ion satellite carriers.
You can consider the rocket as a bus delivering all the payload at the terminus, at the bus stop, and we are like a taxi cab, taking all those passengers on board our vehicle and delivering each one where it needs to be.
We know where we are starting from, and we know the trajectory we have to follow. So we know when we have to ignite our propulsion system and in which direction to reach the perfect spot. And once we are there, the satellite is ejected out from the ion satellite. If very small satellites, so like the CubeSats, there is a spring that is compressed inside the tube, and once the door opens, the energy of the springs can be released and the CubeSat is ejected outside. If we are talking about bigger satellites, in that case we have a mechanical system that detach the satellite into orbit.
It was in 2020 that we launched our first commercial mission, which was a great success and made a lot of noise in our community because our solution is the first space tug, as it's called.
This first proof of concept mission precisely deployed 12 Earth observation satellites. Since then, D-Orbit have launched several more space tugs as part of the ramping up of operations. It's estimated the ion carrier can reduce the time from when a satellite is launched to it being operational by up to 85%. It can also be used to deploy constellations, and the efficiency it brings can reduce launch costs of these operations by up to 40%. It's still very much a process of evolution as the team make use of what they learn on each mission to continually improve the performance and capacity of their vehicles.
we are not just releasing satellites with our Ion satellite carrier. We are also allow customers to test their own experiments directly on board our Ion.
Traditionally, it's taken years from construction of a satellite to its launch. Now it's possible to book a slot and have your satellite launched within just a few months.
Where we are now is really at the inception of a completely new market that follow different trends, follow different rules. The new market is global. So European companies have access to US market, the US companies have access to Asian market, and so on. It's going to grow so fast.
The average age of the people in the company is 30, probably even less than that.
When we started the company 10 years ago, we were just 2 people and in a small office with just 2 desks. Nobody was talking about the new space economy. And now we are a team, I would say a rock star team of 130 people in 3 countries.
With so many satellites being launched, it means that there will also be a huge increase in the amount of data that is being collected.
And in most cases, you find out that like 60 to 70% of the data is not usable. It's like when you take the picture with a phone. You take 20 pictures and then only 3 are saved in your phone. All the others are not good, right? So pretty much the same.
Approximately 10%, I think, of global CO2 emissions comes from data centers. The amount that we use data and process data is because of all those computers, which need a lot of power, and then they need to be cooled, and that uses a lot of energy. We're collecting lots of data in space now, so why don't we export this capability to space, where we have abundant free power, the sun, and don't have the problem of cooling in the same way that we do on the ground.
Currently, many orbiting satellites only have a brief window to be able to download data to ground stations, where it then needs to be processed, meaning it can often take hours to receive vital information.
What we've decided to do is try and solve this problem by putting much more compute capacity in space nearer to where the data is being collected. And what that means is that we can process that information immediately and select the really important parts and downlink those really fast.
Smaller data packages means that you can use different mechanisms to get the information back to Earth, such as sending messages via geostationary satellites.
Another revolution that's happening in space at the moment is Internet of Things from spacecraft, which are enabled by constellations of satellites which are able to pick up signals from tiny devices on the ground, which are powered just by a battery that can last several hours. Now, those support very small messages, but on a regular basis. We can also cross-task other satellites. So what I mean by that is when satellites are scanning in a wide mode, they can look over a very broad area. But if they're able to spot something's amiss, you can then task it or another satellite to zoom in on that area and look for much more detail. So that needs an immediate response cycle to be able to do that. So this is a real game changer in terms of adding capabilities to existing space networks.
And on some new satellites, such as those to be launched by Aurora Tech, there's the capability to do their information sifting on board.
You can imagine it like this. We detect a fire on the ground. A graphics card on the satellite is processing the data, and then we can immediately send that data, the meta information, down via a satellite relay network and have the information on the ground within a couple of minutes.
The number of planned satellites is expanding at an extraordinary rate. In October 2021, Rwanda alone announced its own mega constellation, which could contain over 320,000. But do satellites have the potential to be the architects of their own demise? Since Sputnik, the world's first satellite, reached orbit in 1957, it has been followed by over 11,000 others. These in turn have contributed to vast amounts of debris, otherwise known as space junk. But the problem is that no one knows for sure how much, as current technology is only able to track pieces larger than 10 centimeters across. At the University of Texas in Austin, Moriba Jah and his team are involved in a groundbreaking project aimed at plugging this dangerous gap in our knowledge.
We believe that the sample size, the trackable set, is roughly about 30,000 objects ranging in size from a cell phone all the way to the space station. That's what we can measure, what we can sample. Based on that, we hypothesize that the entire population is probably about 1 million or so objects going down in size to about a millimeter, a speck of paint. So it's like, out of everything we need to worry about, we can only actually measure about 1%, we believe, and of that 1%, only about 4% of the 1% are the things that actually work. So it's crazy, like the amount of trash that's in Earth orbit. There's no stoplight, so things are just crisscrossing each other at speeds up to 15 kilometers per second, so 15 times the speed of a bullet. And so when two objects meet at the same place at the same time, two objects can become tens of thousands of smaller pieces.
Pieces that could potentially cause catastrophic damage to the International Space Station and other satellites. Even the smallest pieces pose a significant danger.
A fleck of paint traveling at 15 kilometers per second definitely penetrates a spacesuit, causes physical harm to the astronaut, might not kill the astronaut, but it's a bad day. When astronauts go out to do their spacewalks, the strategy is hope, because we can't track these small things.
But what about the things that we can track?
If I just look at, what does the U.S. Space Command, have in its database, and I'm just going to click to show all the debris and rocket bodies as well so that we can kind of see what that space traffic map looks like. Now, if I say, well, what is the space traffic map from Russia? That looks really different. There's not a whole lot of agreement or overlap.
In order to create an accessible and comprehensive source of information, Moriba developed a data sharing platform known as Astriograph.
If you have any information about stuff in space, you can deposit it, we ingest it, we evaluate it, and output the combination of these opinions so that people can get a better picture of what's happening in space.
Moriba and his team are also working on a way of identifying objects in space using photons of reflected sunlight to create a digital fingerprint.
This is a model of a dead satellite called Topex, orbiting the Earth roughly at around 800-kilometer altitude. The photons that get scattered look like all these dots. If I just click on one, it'll basically tell me where did that light get reflected off of and how many packets of light per second. So this is saying I counted 8,566 photons, in that 1 second, for instance. You can't manage what you don't know. You don't know what you don't measure. So measuring is the foundation. My whole thing, and part of the motto that I have for my research program is Latin. It's nihil arcanum est, which loosely translates into nothing hides, nothing remains hidden.
But a space debris database can only be as good as the information that's available.
There are systems in place for detecting this, but they're quite crude, and it involves radars on the ground. Now, these weren't even designed for detecting debris. It was actually designed for detecting incoming missiles. We have information, but the precision of it provides a lot of room for error.
Putting dedicated debris detecting telescopes into space will be costly and time-consuming. But by using their navigation cameras on the ION satellite carriers, Simon and his team hope to provide a way of collecting new and meaningful information about debris. They have also created a bolt-on deorbiting device which can be attached to future spacecraft to avoid adding to the problem after they are decommissioned. Before he joined D-Orbit back in 2018, Simon Fellows was the project manager of an extraordinary experiment. It involved leading scientists, engineers, and a consortium of companies, and was led by the Surrey Space Centre at the University of Surrey in the UK. Its mission was to test technologies aimed at removing space debris, all of which were housed in a 150-kilogram satellite platform.
We shipped it over to America, where it was loaded onto a Dragon capsule and delivered to the International Space Station in a box. We had a live link with the astronauts as they were unpacking. We were able to give them direction and information about which panel to take off next, and just to be there while they did it.
Once assembled, the platform was placed into an airlock and then deployed into space by a robotic arm.
And after a certain amount of time away from the International Space Station, then it could turn on and start activating all the different control mechanisms on board. So there's no propulsion for orbit raising or changing, but there was attitude control. Because we're in space, you only need a tiny force to actually make a change to the orientation of a spacecraft. So they had magnetorquers, which are electromagnets to bounce off the Earth and the Moon's magnetic poles and actually position the spacecraft by using magnetic force, but also reaction wheels, which are like flywheels that spin up and spin down and can actually control the orientation of the spacecraft. So the first of the tests was the net experiment. We shot out a CubeSat from the platform, and this was the target for the net. So the CubeSat goes away from the spacecraft and at a set time starts to open up panels and starts to inflate booms. We were trying to copy a 1 meter cubed spacecraft, and then the net's fired, and the net had these 6 motors around the outside edge, and at a set time, the motors actually draw a string around the net to close the net. So we captured it all on camera on the spacecraft, but actually getting the video down took a couple of days, and every day you'd rush to work and say, well, what happened? You know, we know the spacecraft's okay, but did the net catch? After a couple of days, we actually had the complete video. And so seeing it for the first time was incredible, absolutely amazing. And there are plans to scale it up. And there's a very large spacecraft about the size of a double-decker bus. It certainly was in mind when the net was designed.
They also successfully tested a visual-based navigation system which used LiDAR in combination with a camera.
And this is a really important technology to demonstrate, again, in space, because in order to catch something, you first need to understand how it's moving.
The next experiment was a harpoon, once again a scaled-down version of a device intended for large satellites.
The harpoon was fired using cold gas. We hit the target, and everyone gets very excited about that, but actually there's a lot of information that's learnt, even from the tether dynamics, the way the tether moved on orbit for that short amount of time.
The final part of the mission involved deploying a drag sail to make the platform deorbit, so it would burn up upon re-entry into the Earth's atmosphere.
We've got the stepping stones together now, but if we could link things up, so if you had the visual-based navigation somehow tracking an object, so hitting the target, which is stationary, is one thing, but hitting a target that's moving is like a quantum leap.
This is the mission control team who are hoping to make just such a leap with a debris removal craft called ELSA-D.
So ELSA stands for End of Life Services by Astroscale, the D for demonstration. What ELSA is doing is the end of life where the debris spacecraft has been prepared with a docking plate. And that's a special magnetic docking plate with markers on it. So our services spacecraft will go up, it can work out the orientation of the debris spacecraft using those markers, and it can maneuver itself to then capture with the magnetic force that prepared spacecraft.
The mission reflects the growing international nature of the new space industry.
We have the mission control team here in the UK, so that's operations and ground segment. And then in our Tokyo office, we had another control center with all the subsystem engineers. So this is the team that designed and built the spacecraft. So the launch vehicle goes up with quite a few other spacecraft at the same time, and they drop us off into the right orbit. At that point, the onboard computer boots up. It's just like switching your PC on. Goes through a set of commands and procedures that it runs, turns on the transmitter, and what we were doing was really waiting to hear the first signals coming down from our new spacecraft. Everything that the whole company had been working towards for several years really was coming down to that one moment, that first pass. And I think that was a tremendous moment for all of us when that happened, when you see the telemetry come in for the first time, everything goes green, and you know the spacecraft is alive. So what we have here is a 1:2 scale model. In other words, this is half the size of LCD currently. So the actual spacecraft itself is about the size of a large refrigerator. This is the servicer spacecraft, and this is the client spacecraft that we use to simulate a piece of debris. You can clearly see the solar panels there on the side. They provide power to the spacecraft. And we've got a number of sensors. So the star trackers and sun sensors on the spacecraft, they allow the onboard computer to work out what direction the spacecraft is facing. If we need to rotate it, there are spinning wheels inside called reaction wheels. Or if we need to move it faster, which we will do for the capture, then we use thrusters at the corners of the spacecraft, and they fire pulses of gas, and they can cause the spacecraft to rotate or move as needed. So the client spacecraft will be pushed off from the servicer. It will come out and it will be left free floating. It will be under control at this point, so it has its own set of actuators on board to keep it stabilized. When we come to do the capture, we'll be thrusting the servicer closer to it. So as it approaches, the magnetic capture will kick in just like that. Yeah, you hold your breath. All we see is telemetry coming down at that point. We have laser rangefinders, so we know what the distance to the client spacecraft is, and you're watching that increase, and then you're hoping that it decreases again. What you don't want to see is that line just continuing as the thing drifts off into space.
In August 2020, this first part of the mission was successfully completed.
We couldn't have asked for a smoother demonstration. I think everyone was very pleased when that went off without a hitch, a big sigh of relief, and then straight away really we're preparing for the next phase.
The most crucial and challenging part of the mission still lies ahead.
We're going to make that debris spacecraft start tumbling as a real piece of debris would do, and we're going to maneuver our servicer spacecraft to capture that while it's tumbling, because if we're going to clean up the orbital highways, so remove debris that's up there, we're going to need to be able to do that autonomously in orbit. So when we're looking at a piece of tumbling debris, there are visual cameras on board. They will take a series of images of that, downlink it to the ground where we have image processing software. That allows us to work out the tumble characteristics of the debris spacecraft and then upload a maneuver command to start that, what we call the dance. So literally the servicer spacecraft dancing around the tumbling debris. From that point on, once we've commanded that start, it's autonomously done on board. There's simply not enough time for human beings on the ground to see the telemetry, react and command it. The onboard computer will be calculating several times a second from all its sensors. It will fuse all that data and it will work out how to keep firing each of the 8 thrusters in order to maneuver itself around. It's going to be a world first when that happens, because there has to date not been the docking of essentially uncooperative and non-communicative other spacecraft.
At the end of its mission, ELSA-D will slow its orbit, causing it to re-enter the Earth's atmosphere and burn up. But in the future, commercial versions will release their captured satellites safely below the space station and then return multiple times to collect other redundant satellites.
And in 10 years' time, this should be the routine activity that we'll be able to look back on the decade previously and say, yes, it all began with S02E.
As we expand our activities in space, it's not just technology that's required. We will also need rules. One man who understands this more than most is Professor Frans van der Dunk, one of the world's leading experts in space law.
The interesting question about space law, and in that sense it's basically part of international law full stop, is that there is no single person or entity in charge of making the law. You should realize that outer space, basically like the high seas, is an international area where no single state can determine the legal regime. And in terms of enforcement, you run up against the same problem as with general international law, that there is no overarching enforcing authority.
At present, much of our activity in space is governed by a treaty negotiated at the United Nations and ratified by over 100 countries. Known as the Outer Space Treaty, it dates back to 1967, just 10 years after the launch of Sputnik, and when the Cold War was at its height.
What is obviously very conspicuously missing there is the attention to potential commercial, down-to-earth, practical applications. And that is probably the largest problem that we are facing today in legal terms. For every business opportunity, the most important point is to have legal certainty in advance. There's also a growing realization that private enterprise is, of course, only interested ultimately in its own financial well-being. And part of what we're doing right now as space lawyers is actually trying to fill that gap in the best possible way. So create the best balance between the bona fide interests of bona fide private entrepreneurs without destroying the environment or the social coherence or international solidarity and things like that. That's the task ahead of us.
At present, nation-states are financially responsible for any consequences that arise from missions that are launched from their territory.
So if the launched satellite or the launched vehicle crashes into a neighboring country and causes $100 million of damage, the $100 million of damage claim will be put at the doorstep of the government and not of the private entity or person. And this, of course, means in turn that any half-smart government which wants to allow these things from happening in the first place has a national space law in place, including a licensing system.
But even with a technically rigorous license, governments also expect space companies to cover the financial risk, which means the space insurance industry is also expanding. But if it's your satellite that is damaged by someone else, how easy is it going to be if you need to make a claim?
If it's a big satellite which has been launched a year earlier, you'll probably have a pretty good chance of identifying the launching state and thereby the state which has to pay for your damage. But if that satellite has been fragmented into 20 pieces 5 years ago, and it's one of those smaller pieces which hits you, it might be very difficult to retrace the path of that fragment to the original satellite and thereby identify the actual liable state. You probably need a major accident to really make everyone aware how important this issue is and how much better it is in the long run to spend a little bit money up front to prevent these accidents from happening, or at least bring down the frequency with a major factor. Pay a little bit extra up front rather than be facing those huge risks afterwards.
So if the satellite revolution has already started, what comes next?
There are already projects in place to deliver small satellite constellation to the moon. As we have a global positioning system on Earth, we're going to need one on the moon if we want to deploy infrastructure on the moon to get raw materials.
If we go to the moon and we can mine ice on the moon, we can use that ice to refuel spacecraft. We can also use it to basically provide water and oxygen for humans who want to live in orbit of the Earth. And in orbit of the Earth, then we can start doing exciting things like in-orbit servicing and manufacturing.
the sky is literally open to us. We can build then the space stations, we can move also the factories out to space.
There's a whole host of products we can make in space, and some of those products will be used on Earth, and many of them will be used in space.
We don't build boats on deserts and then move the boats onto the sea. It's so obvious that we are going to build spaceship in space directly. It's just a matter of when. And the answer to when is when there will be someone ready to buy them. At the end of this decade, we will have all the capabilities that are required to start the interplanetary economy.
But also, unless we treat space carefully, we're going to be our own worst enemy.
My hope is that enrolling the rest of humanity in this vision of space environmentalism say, hey, have you noticed the night skies and how there are more dots moving across the sky, these sorts of things? Would you like to have a say in that? You know, promote this idea of environmentalism to maintain this environment, you know, for many generations to come.
We're probably in the most exciting point of human history right now. I'm confident that by the end of this century, humanity is going to be looking at exiting the solar system. We're about to see a very, very rapid transformation in terms of how we do things and where we go.